against them. And so you have an effective osmotic pressure that packs those nanorods together, or whatever kind of rod. So entropy can give us these nice assemblies, but it does not tell us how they're oriented with respect to the substrate. For that, we need some combination of dynamics and enthalpy. Because we're working in a nonpolar system, we look at the van der Waals interactions between all the components of our system. So the substrate, the solvent, the nanocrystals, and the ligands that are attached to them. And Asaph Widmer-Cooper and Phil Geisler did molecular dynamics calculations to calculate the exact forces between each of these components. And they plugged them into a Monte Carlo simulation in which they could watch the nanorods start to pack together. And what they saw was very similar to what we were seeing experimentally. So to get the nanorods to align experimentally, we needed to be able to control this parameter space. First, we needed to engineer a system that would independently control the temperature of the system and the vapor pressure, or the evaporation rate. We also needed to select appropriately the substrate, the solvent, the nanocrystals, and their ligands. And if we got all those parameters right, as I said before, we could see nanorod alignment. And at the point when we started doing this research, there were 3 groups that had demonstrated nanorod alignment previously: Dimitri Tlapin, Kevin Ryan, and Tom Russell. But they had all demonstrated alignment on a very small scale of hundreds or thousands of nanorods, less than a square micron. And our goal had been to scale this to a square centimeter, and we weren't using the same techniques that they were using. So this is 8 orders of magnitude, and the first thing we noticed as we began to assemble these rods and have a little bit of success was that it was really difficult to quantify how much success we were having. Zooming all the way in, we could see, yep, here are 100 or 1,000 nanorods, they're well aligned. But as we began to zoom out, we lost resolution of those individual nanorods. In order to optimize and scale this up, we needed a quantification method that at that time didn't exist. So I collaborated with the Stanford Synchrotron Radiation Laboratory to come up with an X-ray diffraction technique that, for those of you not well versed in X-ray diffraction, it's a very simple technique. Imagine that there's white light coming in a window and it hits a prism. It gets split into all of its color components. But in this case, we're using X-rays, and the X-rays only have one color. So let's go back to the light coming in the window, but let's say the light is only green. It still diffracts at the same angle that green light would diffract if all of the colors of light were coming in. And if we turn the prism 90 degrees, the spot that is green gets also turned 90 degrees. So you can see that if there's anisotropy in the system, you can track where that diffraction is happening and see, in this case, how the prism is oriented. Our cadmium sulfide nanorods have an anisotropic Wurtzite lattice that allows us to do very much the same thing. So you can see on the left-hand column data for unaligned rods, and on the right hand data for aligned rods. The left, this dark circle, is where we're seeing diffraction events. And you can see they happen at all angles, meaning that rods are standing at all different angles. Whereas in the case of aligned nanorods, they're occurring up here and down here. And this is from a different diffraction event in the crystal, a different crystallographic direction. And so we can turn these into histograms of how many rods are oriented at each angle. And what we see is in the case of unaligned rods, the histogram is rather flat. And in the case of aligned rods, we have a sharp peak at 0 degrees, or perpendicular to the substrate, and smaller peaks laying flat against the substrate. And we can see that the rods don't like to do much of anything in between there. The fundamental concept behind this method is elegantly simple, but quantifying it makes the details appear, and they're very complex. People had used the same sort of technique to look at things qualitatively before, but they had never been able to quantify it. So after studying this for a while, we found that we needed to take this diffraction data at 2 sample geometries, one at grazing incidence and one in the specular geometry. We then stitched these 2 data pieces together, and then we had to apply 3 correction factors. One correction factor accounted for the fact that diffraction is happening in 3 dimensions, but it's being projected onto a 2-dimensional flat plate detector. The second correction is for any polarization of the incoming X-rays, which at a synchrotron radiation laboratory is roughly 98%. Finally, we had to correct for any absorption of those X-rays that was happening in the film. So after developing this technique, we realized that it was applicable to really any sort of thin wanted to investigate the morphology. And this has since been used on a variety of organic and inorganic thin films, not just nanocrystal films. Using this technique, we went back to our nanorod alignment and we tried to look at which types of substrates we could align on. And we found we could align on a variety of device-relevant substrates. But some of the alignment was much better than others. You can see these peaks indicating rods are laying down on this one, and you don't see any rods laying down on some of these substrates. And so we could map out the entire parameter space by looking at the degree of rod orientation as a function of temperature. We found that temperature did help them reach alignment, which was in keeping with what happens in pneumatic phase transition in liquid crystals. We also found it was difficult to align rods the longer they get, which was consistent with the fact that the rotational diffusion constant gets slower and slower the longer those rods get, and it's just kinetically difficult to align these very large rods. Finally, we plotted the degree of alignment as a function of the substrate Hamaker constant, or van der Waals coefficient, and we were able to develop a heuristic for the best alignment. This heuristic was that we wanted the Hamaker constants of the system components to fall in decreasing order, starting with the substrate and the solvent and then the ligands. Using all of this, we were able to align on 1 square centimeter 96% of the nanorods. So we've now accomplished this goal of getting something that's starting to look like device size, that's a thin film, single crystal semiconductor. So we can check this box for achieving the geometry, but now we have to make it look like a solar cell. And in a solar cell, we need some sort of asymmetry that induces the electrons to move only in one direction, otherwise they'll cancel each other out. And one common way to do this is to use a heterojunction. A heterojunction is simply the union between two materials. And when you engineer that to have the right band alignments between all of these materials, you can manipulate the flow of the electrons in your system. So heterojunctions are useful in things such as light-emitting diodes, catalysis, sensing, photovoltaics, and water splitting. In this transmission electron microscope image, you can see an epitaxial heterojunction where two lattices are coming together. And the lattice is simply the atomic spacing in the crystal. But no two lattices have exactly the same lattice constant. And that means that when you bring them together, there's going to be lattice strain due to one lattice being a little bit bigger than the other one. This strain is relieved over some characteristic distance in a misfit dislocation, where one bond is left hanging. And this misfit dislocation degrades the performance of any of these heterojunctions because it's a defect at our interface. So let's imagine we take two materials that have fairly low lattice mismatch, and now let's shrink their interfacial area, let's shrink the heterojunction, to be smaller than the characteristic distance over which we have a misfit dislocation. If we could do this, we would have effectively a perfect heterojunction with no defects at the interface. And in nanocrystals, it is possible to do this. Shiazawa et al. Showed this in bulk systems, or large-scale systems, in 1968, and recently Sattler et al. Showed it using cadmium sulfide nanorods. So in his experiment, he had cadmium sulfide nanorods floating in solution, and he added in copper ions. It's energetically favorable for the copper to trade out with the cadmium, and this happens selectively from the ends of the nanorod. So in this false color image, the blue is copper sulfide, and the yellow is cadmium sulfide. And I'll note that this is generalizable to a variety of chemistries. You'll notice that in this image, most of the rods have blue ends. So we have copper sulfide coming in from both ends. And this doesn't give us the asymmetry we need to drive the electrons in one direction. We need there to be only one end that's copper sulfide, one end cadmium sulfide. But even if we were able to get this system to look like a heterojunction that is asymmetric, we still wouldn't have any guarantee that they'd all be pointing in the same direction when we assembled them. And if they cancel each other out, we're not going to get our photocurrent. So we hypothesized that if we use this method developed by Sattler et al. On our substrates of aligned nanorods, and we just dipped that substrate into a solution of copper ions, that they would exchange selectively from the top, or exposed end of the nanorod. It was pretty straightforward to carry out this experiment, but analyzing whether or not we had gotten what we hoped for was a little bit trickier. For that, we used Rutherford backscattering spectroscopy.